Example 3 walks us through how to do a long cylinder. So a long cylinder, figure 2.21, carries a charge density that's proportional to the distance from the axis rho equals kr. Ooh, they're getting fancy here. So let's draw what that looks like. So we have a long surface, a long cylinder. So it goes on for a long time. And the charge per unit volume is rho is equal to kr. So it gets thicker the further you go away from the center. Find the electric field inside the cylinder. So we draw a Gaussian cylinder of length L and radius r inside of here. So let me draw the axis actually of this cylinder. I need to get a straight edge. Well, that was pretty straight. So we draw some small Gaussian surface and we try to keep it a distance away from there. And this is length L. And this has a radius r. Hard to see there. And because it's far away from the edges, we know that none of the flux is going to pass through the ends. The enclosed charge is equal to, so let's use a different color here for math. So Q enclosed is equal to the volume integral of rho times d tau. And in cylindrical coordinates, that's going to be the kr is the rho. We're going to use prime coordinates here for the integration because it's going to be different than the Gaussian surface that we're going to do shortly. And for cylindrical coordinates, r dr d theta dz. Obviously, we're traveling with the z in the longitudinal direction here. And solving that is a walk in the park. So we have 2 pi k L. Where did L come from? Oh, that's the length of the box. 2 pi k L. And the 2 pi came from the integral of d theta because we're going all the way around. The dz, we went direction the length of L. And that's going to be, the leftover part is r prime squared because these two multiply together. dr, well, if you've never seen that integral before, you're kind of hopeless. So that's just 1/3 r cubed. So it'd be 2 pi k L over 3 and r cubed. Okay, so that's the amount of charge that we've actually captured with this varying charge density. The next question we have is, what is the electric field? And we're going to tie the enclosed charge to the electric field because this is all going to be equal to the surface integral of E dot dA of the enclosing surface. Well, symmetry provides us a clue that that electric field is going to be constant. It's not going to vary as you go around the surface. And the integral for this one is going to be some small r. So it's 2 pi. I'm sorry, dA. We're using the same dA up here that we used before, so we get basically the magnitude of E is equal to 2 pi RL. 2 pi RL is the electric field, or the total flux. So now we have this equal to that, and so we have E times 2 pi RL. Is that even off the screen? That is. Equals 2 pi KLR cubed over 3. Well, this cancels, that cancels, that cancels. One of these cancels. This cancels, that cancels. So we get E. The magnitude of E is equal to, did I cancel the 2? 1/3 epsilon naught. Oh, we forgot epsilon naught at the bottom. Epsilon naught. And we have a k left over. And then we have r squared. And the direction this thing is pointing is in the r hat direction. There, we've solved it. The electric field using very simple integrals and using Gauss's law.